All right, we are now on to page number 6. Hopefully this says parallel circuits. Now, guys, I'm pretty happy with the activity that we did in our last lesson. You were confirming a few things. In a series circuit, the current should be the same all the way through, which leads that the voltage drop across each resistor is going to add up to what? Could you raise your hand and tell me what that should equal? Yes, Hamdorf. The EMF, which is the voltage provided by the power supply. This is important because now things are going to get a little bit trickier. Parallel circuits are a little bit more difficult, okay? But it still obeys all of the laws. Kirchhoff's law is obeyed here. We spoke about this, but let's just draw current flowing through a wire. It splits into two different channels, possibly channel 1 and then channel 2, and then it recombines such that the flow of charge in equals the flow of charge out. Okay? And we should know that the current through channel 1 plus the current through channel 2 equals the total. That is conserving charge. Okay? Now, what we're going to add to this, though, is if I go V equals IR, if I multiply that by the resistance, I get the voltage across resistor 1. And if I multiply I2 by R2, then we should get the voltage across resistor 2. Okay? But, shock horror, this is important, and I didn't want to do that. This is important, and we will confirm this with an experiment tomorrow, that no matter which channel your electrons pass through, they lose the same electrical potential. That means, Spencer, the voltage across both resistors will be the same. Okay? So our little electron that comes in full of electrical potential with lots of squiggly lines, let's go 3 and 3, doesn't matter which one he goes through, when they reconvene and they compare each other, they have lost the same amount of electrical potential. The analogy here is, let me just finish this analogy. Oh, he just gained electrical potential. Only 4 lines. So, the analogy here is, Hugo, I do not appreciate you talking. Sorry. In the canteen, this makes more sense, that you have one line flowing into the canteen and one line theoretically flowing out, but there might be 3 different checkouts. They would be 3 resistors all in parallel. And it doesn't matter which checkout you go through, you will lose the same amount of money per student. So each kid goes in and buys his sausage roll, and when they come out of the canteen, they have lost the same amount of money per checkout, because each checkout had the same voltage across. Okay, it'll make more sense as we go through some examples. Okay, so it's important, and we will look the voltage across them always going to be the same. So I could throw some values in. Let's just say it was a 2 volt drop across voltage 1. It would be a 2 volt drop across voltage 2. Now, let's add Kirchhoff's law here. So we have I total equals I1 plus I2 plus I3 for as many different channels you have. And then we're going to substitute in Ohm's law here, and I'm going to write it as V total on R total equals V1 on R1 plus V2 on R2 plus V3 on R3 plus ... So, since all of the voltages are the same, I can then cancel them out. We would have a common factor of V outside of, and the equation becomes 1 on R total equals 1 on R1 plus 1 on R2 plus 1 on R3. Okay, and this is what is provided in your data sheet. Because the voltages would be the same. I could write this as V outside of 1 on RT equals V outside of 1 on R1 plus 1 on, and then you cancel and cancel because you've got a common factor of V on both sides. Okay, so literally, if your voltages are the same, which they will be, we will confirm via experiment tomorrow, you get this equation. So, interestingly, if you put two resistors in parallel, let's just go nice, easy example. Two identical resistors, and you put them in parallel. The actual total resistance is a half. It's half because they're in parallel. Think about the canteen. If you add an extra channel, there's less resistance in that circuit. You've got students could go through that checkout or they could go through that checkout. You're giving the electrons options. So by adding another channel, you're actually reducing the resistance. So in series, you would increase the resistance by adding them in series. But if you were to place them in parallel, because it's the reciprocal, it actually drops. So let's look at a very simple example of a couple of ohm resistors. Could you please draw the following circuit, or at least the section of a circuit? 2 ohms and 2 ohms. And let's say we have total current equals 1 amp. And we know that the total current would flow out as 1 amp. Now, here, gentlemen and ladies, we could say that we could look at the ratios and you could pretty much figure out how much would flow through each. Would somebody like to tell me how much current would flow through each channel? Are you being silly, Cooper? No. Have a look at the... half an amp each. Okay, they would split such that half of the current would flow through. Okay, please guys, shush. Now, let's just quickly do our equation here. We're going to go, let's find the total resistance. We've got to start with the reciprocal. Yes, Varad?
So does that then change if the resistance is different on the top with the ratio?
Yes. So if we change, then it gets trickier. We're not going to use a ratio. We're going to use this equation here. Okay? 1 on RT equals 1 on R1 plus 1 on R2. We'll go equals 1 on 2 plus 1 on 2 equals 2 on 2. So 1 ohm, equals 2 on 2. Therefore, our total, we flip that fraction, you get the same. You're going to get the inverse of 1 is 1. So 1 ohm. So have a look at that. You can put two ohm resistors in parallel and the total resistance is a half. The equivalent resistance, remember my big red curtain. I could bring up the big red curtain, right? And if I measured the voltage across and the current through, I could say whatever is behind that curtain has an electrical resistance of 1 ohm. But I've got no idea what's behind the curtain. It could be a half ohm and a half ohm in series, or it could be a 2 ohm and a 2 ohm in parallel. The electrons don't know. They just know the rate that they're flowing in and how much energy they have lost per unit charge. Now, let's get to something that is a little bit trickier when they are not the same. Actually, no, let's just confirm our voltage drop first. Guys, our volt... If you have the room, please. V1 equals I1 R1.
So if you have 4 ohms resistance total, ohms resistance.
Could you just write this down, please, Cooper?
Yeah.
Thank you. You writing this down, Varad?
Yeah.
Thank you. Now, again, I made these values up, but they are correct. Again, there would be a 1 volt drop across the bottom resistor and a 1 volt drop across the top resistor. So again, it doesn't matter which way the electrons travel. Each coulomb of charge that flows loses 1 joule.
That's a
we could check. Remember I said that we could put that big red curtain up. Don't do this, but put up the curtain and go, all right, if I'm detecting a 1 ohm resistor and 1 amp of current flows through it, then the equivalent voltage is going to be the total current times the equivalent resistance, and we end up with a voltage across of 1 volt. If we didn't know what's behind this, and I told you that there's 1 ohm of resistance, all right, if I said V equals IR, we get the same voltage drop. So I didn't even know what was behind the curtain, but I could tell you all 3 things about the voltage, the current, and the resistance. Okay? It will make more sense as we change the values. So can I now get you over on this? Ooh, let's go down the bottom here. Hopefully you have space still on page 6. Let's get 1 amp flowing in. And now let's change the resistances up. Let's go a 4 ohm and a 3 ohm. Such that 1 amp flows out. All right. Now again, you need to approach these questions with the same sort of steps. Step 1, we need to find the total resistance of this junction. So step 1, I'm going to find R total. So 1 on RT equals... So we'll go 1 on 4 plus 1 on 3. Now, you can do this in your calculator. You could just calculate fraction button plus fraction button raised to the power of -1, and that would give you R total. But with these, we need lowest common denominators. That's going to be 3 on 12 plus 4 on 12 gives 7 on 12. Now, this is still the inverse. We've just found out that the reciprocal of RT is 7 on 12. So I would just ask you to flip both sides. That's the easiest thing to do. Flip both, and then you can say, therefore, RT equals 12 on 7. Okay? And so that's fine. You will generally be given nice numbers. Sometimes if you've got 3 or 4 resistors of varying values, it might be a bit tricky to find the lowest common denominator, and it might end up becoming 5,327. But if that's what it is, you add them up and then flip it. So our total resistance is that. Let's just evaluate that. It's 1.71 ohms. Okay? Now, normally you would have the voltage across. We don't have that. But let's just confirm. I could bring up my magical curtain and say, look, whatever's behind that curtain, we've just found out has a equivalent resistance that's equal to 1.71 ohms. Okay? That's it. That's what we said. We don't know what's behind it, but the equivalent resistance behind that curtain is 1.71 ohms of electrical impedance. So I should be able to find the total voltage. That's just going to be I total times R total. In this case, this is the total resistance. So we'll go, all right, I know that 1 amp flows through, we'll get a voltage drop of 1.71 volts. Okay. Oh, 1.71. Okay. Now, here's the thing. Using this parallel voltage drop rule, that the voltage across all channels is the same, I can now get rid of that curtain and go, all right, if I now know the voltage across the entire channel, I know that the voltage across here is 1.71 volts. And then the voltage across this bottom one is 1.71 volts. Now, if I have the resistance and the voltage across, what can I calculate? The current that flows through. So let's just check. Kirchhoff's law, I should be able to figure out that the sum of the two currents in each channel must add up to a total of 1 amp. But let's just check. So let's go, the current through channel 1 equals V on R, V equals IR. I'm having a mental blank. V equals IR, I equals V1 on R1. That's going to be 1.71 on 4. And then the current through channel 2 equals V2 on R2, which is 1.71 on 3. So would somebody mind, I haven't solved it. Would somebody mind solving that for me, please?
0.574.
0.57.
Oh, sorry. No, that was for the 1.7 over 3. 0.57. So the second one. The first one is 0.43.
Now, this is where, again, these are Sudoku puzzles and we have rules that we're going to use, and then there are rules that we can confirm that we've got the right answer. I can use Kirchhoff's law here to confirm that the current flowing through both channels must add up to the total, which it does. Okay? So we're keeping account of all of the charges that flow. So all that we added is that the voltage across each resistor is going to be the same, and we could find that. Okay? Couple more examples. All right. Could we please consider the following? Let's sketch this diagram and figure out what's happening. We've got a 2 ohm and a 4 ohm. We've got a 12 volt supply. Okay, so now we're going to follow the steps that are on the previous page. Okay? And my battery is slowly dying, so I hope if my battery dies, I'll need you guys to help me out with calculating some things. All right. Step 1, we need to find the total resistance. So we use our resistance in parallel. 1 on 2 plus 1 on 4. That's 2 on 4 plus 1 on 4 equals 3 on 4. Therefore, we can flip both sides and that will give us 4 on 3. 1.33 ohms. Okay?
We're not leaving fractions, sir.
We generally don't, because that's an irrational fraction. There might be a slight rounding error. Just by me rounding to 3 sig fig, there may be a slight rounding error at the end. But you're right. If we left it as a fraction and then placed that fraction in another fraction, you'd keep the same answer. But let's just do intermediate rounding to 3 sig fig. What does step number 2 say on the previous page? Cool. IT is going to be the total voltage divided by the total resistance. So we've got 12 volts over the 4/3 bits. That gives 9 amps. Okay? Now, let's just add what we know about this circuit. I know that 9 amps flows out of the battery and 9 amps will flow back towards the battery. But at this junction, it's going to split such that I1 plus I2 equals 9 amps. Now, logically, who's mumbling? I can hear someone mumbling. No? It was you?
wasn't me. I was there.
Why? Who's mumbling? I'm asking a question. Who was it? Grow some balls, guys. Asking a question, I want an answer. You can use logic here, and looking at this, the greater the resistance, the less current will flow. It makes sense. If you've got a checkout lady at the canteen who's a little bit slow, maybe she's just started, she's forgotten her password, she doesn't know the code for a sausage roll, you're going to get less students flowing through that channel. And the canteen lady that's been there for 40 years and is just, boop, 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 how are you, Stephen? How's your dad? Blah, blah, blah. Hello, Mr. Sisson. How you doing? You know, you're going to get lots of students flowing. But I don't want... I don't want you to try and do a ratio method, because the ratio method will work for simple numbers. But it won't work when you've got a 4.37 ohm resistor and a 52.1 ohm resistor and then a 13 ohm. It won't work. Okay? So you're going to use this method at all times. Now, I know that the voltage in this simple circuit, I know that there are 12 volts of potential across that one and 12 volts of potential across that resistor, because there is nothing else in the circuit that's taking energy. All right? There's no resistors between this junction of the electrons splitting out and this junction where they return back together. There's no other resistance, so there's no other voltage drop. So the voltage across is the total. That's important. So, what does step number 3 tell us to do? Find the current through each channel. So I know that I1 equals V1 on R1, which is 12 on 2 ohms. That gives us 6 amps. And I2 is 12 on 4, which gives 3 amps. Again, I can use Kirchhoff's law to check. Nine amps equals 6 amps plus 3 amps. It is all correct. Okay? So everything is accounted for. All right. Now, was there a step 4?
Yes, combine V across each component in brackets if needed.
Okay, so we didn't need to. We could do step 4 because there was nothing else in that circuit. We didn't have to consider any sums of voltages in series. Let's make it a little bit trickier. Now, in your activity tomorrow, this is as difficult as it's going to get. You're either going to have 2 resistors in parallel or 3 resistors in parallel. And there's only going to be 1 resistor in each channel. Okay? So you'll get either R1, R2, and R3, or maybe you just get R1 and R2. It's going to be simple, and basically it's up to this level. Okay? Let's now go to a trickier example. Okay? Now, in one of those channels, so we'll start off with our 12 volts. Let's just do it off to the left here. We'll start off with our 12 volts. But now, there are 2 resistors in series with one other. So we've got our 6 ohm down there, and then we've got our 3 ohm and our 6 ohm. Okay? Now, I'm just going to leave a gap in the middle. Let's go over here. Step number 1. What is always step 1?
Find RT.
Find the total resistance. Uh-oh. What we've got here, I need to figure out, we need to invoke Thevenin's rule. Alright? Thevenin's rule says that I could replace Thevenin's rule says that we could replace that channel, again, chuck it behind a curtain, we could replace those 2 resistors with one that had an equivalent resistance. what would that equivalent resistance be? 9 ohms. Good. So our equivalent resistance is going to be R1 plus R2, which was 3 plus 6. We could put a 9 ohm resistance in that channel behind the curtain, and everything would continue to flow with the same voltage drop across and the same current through, and you'd have no idea. That's just the one little trick here. But here's the next thing. We know that the voltage across that and the voltage across that must sum to 12. But we don't know what that voltage is, and we don't know what that voltage is. There's so many ways that you could attack this question. It's like a puzzle where there might be 4 or 5 different ways of solving. So, we invoke Thevenin's rule. And let's now find the total resistance. 1 on 9 plus 1 on 6. That's 2 on 18 plus 3 on 18 gives 5 on 18. So our total resistance... here's another thing. Guys, one little rule that you can remember is no matter how high your resistors or how low your resistors are, when they're in parallel, the total resistance will always be less. So if you look at this, if I put a 9 in parallel with a 6, immediately I know the total resistance has to be less than 6. Even if this resistor here was 1,000 ohms, it's still 1 on 1,000 plus 1 on 6, and when you flip it over, you will always get a number less than 6. It might be 5.9999, but it will always be less. So just remember that in the back of your mind. If you make a mistake and you accidentally forget to, it comes out wrong. If it's greater than 6 ohms, you know you've made a mistake. So when it comes out 3.60, sounds good. Okay? All right, now what's step 2? So our 12 volts divided by 3.60 gives us 3.33 amps. Okay? Now, let's just stop there. We know that 3.33 amps flows out of our battery. It then gets to this junction where it splits. We know that the sum through channel 1 plus the sum through channel 2 must add up to 3.33. We will confirm that in just a moment. And then it recombines. And we have 3.33 amps flowing back to the battery. Okay? Yes, Farad.
I don't really get what your point was about the 6. That had to be less than 6. I don't understand why.
See me after class. I'll explain it to you. Cool. All right, step 3. What's the step 3? Current through? All right, we've got I1 and I2. I1, I2. So we've got obviously channel 1 and channel 2. Now, let's just stray away from this one for now. This one's nice because it's just 1. I know the voltage across the 6 ohm resistor. What is the voltage across the 6 ohm resistor? 12 volts. Have a look. If you're an electron, if you leave the battery and you go through this one resistance and then return, it's that number there. Okay? So it's 12 volts. So let's just solve channel 2 first. Now, here's the thing. I could use my check to actually solve here, but I'm not going to. We could look at that. If the total's 3.33, and I know that 2 goes instantly, 1.33, that's the remainder. But let's just solve it the correct way, because I still want to leave Kirchhoff's law for me. I leave that to the very end, and I use that to check my answer. If I use that now, then I don't have that check. So, what I could do, invoking Thevenin's rule. Let's invoke Thevenin's rule and say that if I placed an equivalent resistor of 9 ohms behind that curtain, I now know the voltage across. It is also the EMF. So I could go 12 over 9 gives 1.33. And then I can check that the sum of my resistances adds up. Okay? Hello, Scotty. Now we're almost there. Matthew and Tom, close it, please. Don't care, close it. It's up here. All the good stuff's up here. Thank you. We've nearly got everything. And with all of these circuits, in a test you might only be asked to solve for 2/3 of the values, but we're going to try and solve every single thing. I now know the current that flows through this channel. It's 1.33. So now I can use Ohm's law. If I just fill in the gaps up here, if I go 1.33, where did my there they are, and 2.00, I now know the current flowing through resistor 1 and 2. So the last step, which is in that list, it says step 4 is find the voltage across each resistor if applicable. Well, yes, it is applicable now, because I now know the voltage across the 6 ohm and I now know the voltage, I went in the wrong way, and the voltage across the 3 ohm now, those are the voltage drops. Get this written down. 4 volts across the first one. It makes sense. If equal currents flow through that resistor, you have a greater voltage drop over a greater resistance, because V is proportional to R. What do you notice about the voltage drops of both of those resistors? They add up to 12, which is what we knew at the start. We knew that the total drop across that channel was 12 volts. So now, here's that final rule. We can use the voltage drop rule. So you can check with the voltage drop rule that V total okay? So this one here was Kirchhoff's rule, Kirchhoff's law. Let's try and spell it right. I don't know, Kirchhoff's. Okay, so this is the great thing about these circuits. You will have those laws or those rules left at the end to confirm that you've done it correctly. Okay? Just as remember as well, once you got to here, you could have used the voltage drop rule. Zach? You could use, once you found this, you go, the sum of the voltage through that channel is 12 volts. If this one is 4, then I know that the remaining 8 volts must be dropped across this one. Remember, it's conservation of energy. But then, if you use the voltage drop rule to answer it, then you don't have that check. So you go Ohm's law, Ohm's law, Ohm's law, Ohm's law, check with Kirchhoff, then Ohm's law, you can check with the voltage drop. Okay? Now, this is the thing. There's no one discrete pathway. The next circuit diagram you might do, and we might find that there are 4 different paths because you decided to do that first and then use this rule to answer that, and then someone else used the different rule, and you might have found something else first. But generally you find if you follow those steps, step 1, step 2, step 3, and step 4, then you're going to get the answers right. Hugo, question.
If you get the wrong voltage and use the voltage drop or the other one, you get followed through or not?
Yes, you probably lose only 1 mark. I mean, what if you stuff this one up and you use the wrong current? Let's say accidentally you use 2 amps instead of 1.33. You get 6 there, and 6 and 6. That won't happen. The only way you get 6 volts and 6 volts is that they were equal resistances.
Yeah.
And if the equivalent resistance is 9, it would be 4.5, 4.5.
It was like
But you're right. Yes, if you make 1 error, you will lose 1 mark and follow through. And that's what makes marking this question in the test. You will get a question in the test that has a complex circuit and it might be worth 6 or 10 marks. They're a pain in the butt to mark if Hugo makes a mistake at step 1 and you stuff up finding the... If you stuff up the total resistance, then I've got to get my calculator out and go, what the hell has Hugo done? Has he done part 2? Okay, yes, follow through marks. Has he done part 3? Yes, follow through marks. Varad.
Why is there resistance 6 for the 3 ohm down below?
Sorry, I've stuffed up. That should say... Sorry. I said one thing. Ah, damn it. I didn't want to stuff this up. I said one thing and wrote another. Sorry. I was solving the resistance through the 3 ohm. And this one here, the resistance through the 6. Damn it, damn it, damn it. This is confusing and tricky stuff. So... It's still right. Oh.
3 ohms equals.
Okay, alright. Was it? Alright, now, try it yourself. You've got 15 minutes. Okay.
Me and Nick got stuck on the medium.
Yeah, with the medium one.
I'm going to invoke Thevenin's rule and suggest that the total resistance is going to be R10 plus R equivalent, because that parallel channel is in series.
So that's what we've done in the parallel. And added.
Yep.
We've done that and we've calculated the actual resistance itself. What we're struggling with is the actual current. We've calculated the current total,
If
but
I
we
know the
can't.
total current, I know the voltage drop across this.
Yep.
I'm then going to play my voltage drop law card and say that the voltage drop across this is the total less that. Yeah?
The what? Okay.
Would you like?
I'll play that.
How about, guys? You're working, please. Come on. All right. Help me out here, guys. Let's just work through this really quickly. I'm going to have to first off find R equivalent. Okay, so my equivalent resistance here is a 4/3 ohm. Well, let's just go 1.33, right? 1.33 ohms. All right, so step 1, I had to find R equivalent first. Then, it's still step 1, find R total. R total equals R10 plus R equivalent, which is 10 plus 4/3, which is 11.33 ohms, which is, yep, you're happy with that. Step 2, find the total current.
1.588.
So 18 volts.
11.33 is 1.588.
All right, we can keep an extra sig fig for now. Now, I now know the current flowing through that is I total. So I can find the voltage across. The voltage across my 10 ohm is I total times R10. So I know that of the 18 volts of electrical potential drop, I know that 15.88 volts is dropped across that one. I can, yep, so that was step 3. Now I can invoke.
So that's why I get the extra decimal place. So I can do that. I was predicting it. Hold on.
Oh, that makes so much more sense.
Why is that? Oh, so then that means that the volts going across there is equal to 2.2.
So I know that V total equals V parallel plus V10. 18 equals V parallel plus 15.88. It's conserving energy. So logically, the remaining energy, what do we get? 2.12 volts. Yep. And now because they're in parallel, I know that it's 2.12 across that one and 2.12 volts of potential across that one. Okay?
They keep changing around. They keep changing the parameters. It doesn't really matter which way it's going.
Yeah, it doesn't matter if I got the arrows the wrong way. Yeah, fun puzzles.
It's got 6 resistors in it.
Thank you, Hamdorf.
Bingo. Which is like, oh god. Oh god. That's not good. Oh, Nick, look at this. This one would have been flying the other way. He's struggling to happen yet. Oh god. Oh god. That's not good. Maybe I would screw with you, bro.
So I've done that, right?
Yep.
Is that correct? I don't think that's correct.
Yeah, that's fine.
But
Yep.
then now I'm going to do that one.
Alright, now, here's the problem. We don't know the current. We know that current through that channel and current through that channel must add up to 1.59, but at the moment we don't know. There is... do you guys hear me out? There's another way to solve this. So, do you want to just... I'm going to explain it to Varad. You can find V parallel without using the voltage drop rule. V parallel is going to be I total times R equivalent. Cooper, are you listening to this? I could throw that curtain up and say, instead of a parallel circuit, I could throw the curtain up and just have a 1.33 there. So now, if I said R equivalent, the total current can flow through an equivalent resistance. That's what the Vevan said. So that's going to be 1.59 by 1.33, and that should give that number there. 2.12.
Wow.
I think.
The fact that it's backwards.
Alright?
So the way you've done your cell would be charged for.
Doesn't matter. Okay. Alright, whatever.
Wait, so I'm still not clear.
I know. So, pass me that box. Yep, whatever. Yep.
3 in parallel.
Right.
Plus,
I just put a 1.33 ohm resistor in series with a 10. Which, if you know the current flowing through that 1.33 ohm, could you tell me the voltage across it?
If I need the current, yeah, I can tell you the
Yeah?
voltage.
Would you agree that the voltage across that would be equal to the current through, which is 1.59, times its resistance, which is 1.33? So we could then say that the voltage across this is 2.12. Now the voltage across that is also 2.12, and the voltage across that is also 2.12 because they're in parallel.
Yeah.
Now, bring this back. If the voltage across that is 2.12, if the total voltage is 18, and this one's 2.12, then the voltage across that must be the residual,
Must be
which was 15 point,
8. Yeah, so yeah, one of those.
15.8. Okay?
Okay.
So,
So was it as simple as going like, okay, in that instead of that being 18, should that?
it's not 18.
It's not 18,
because some
so-
energy's lost here and then some energy's lost here.
Yeah. Okay.
So, for I1, like up here, you would need to know the voltage across. So if that's how we first off treat it as an equivalent resistance.
So
Okay.
you got to find the voltage equivalent of that first.
Well, the voltage parallel would be the total through the equivalent. But here's the thing: if we didn't know that, let's just find out what the voltage drop isn't. What the voltage drop isn't is this value here. Because I knew the total current flowing through the 10 ohm, so I found the resistance across the 10 ohm, sorry, the voltage across the 10 ohm, and therefore 18 equals V1 plus V parallel.
Yeah.
So again, throw up the curtain. Alright, if I just solved that this V was 15.88 volts, the circuit only provides a total of 18. If 15.88 is there, then V parallel must equal your EMF less V10, which is 18 less 15.88. It's 2.12. That's hurting my eyes. Right as.
Isn't that a bit strange? I thought voltage is always the same wherever you are.
That's the weird one. That the electrons don't know which channel they're going through, but they always lose the same. You cannot get an electron that loses a different amount of energy by going through a different channel.
Okay.
That's just some weird pattern in nature.
Okay, I get it. Alright. Thank you.
No worries. Yes.
Why did you use 1.33 and not 11.33?
Hang on. I've just lost my undo function. Something has gone terribly awry. Hold on. What did we say this was here? It was
11.33, but you used 1.33 in most of your counts.
all right.
That's what I'm.
Pass me that eraser.
This one.
All right, guys, gentlemen, ladies, if you do not understand the medium one from step 3 onwards, if you do not understand, I would like you to come up to the front, and I'm going to use my Thevevens curtain ruler to explain this. So please gather round, because that's the total resistance, which is that plus that. All right. Now, gentlemen, I don't know whose ruler this razor is, but we're going to destroy it. Now, we figured out that the total resistance of this parallel circuit was 1.33 ohms. Okay. Now, we also figured out the total resistance was 1.33 plus 10 because it's in series, so it's 11.33. We then said, all right, the total current that flows through this circuit is 1.59 amps. Now, I'm going to invoke Thevevens rule that I could place an equivalent resistance equivalent to 1.33 amps behind that eraser, and the same current would flow and have the same voltage drop across. Now, if I told you that 1.59 amps flows through that eraser and it has a resistance of 1.33, you could tell me that the voltage drop across that eraser is V equals IR. So I know that the voltage drop across is now 2.12. Doesn't matter what's behind that, the electron that comes in loses 2.12 volts per coulomb of charge as it flows out. Now, remove the curtain. Oh look, they're in so I know that 2.12 volts across that one and 2.12 volts across that one. Okay? Not only that, let's go back 2.12 volts. If I know that the total voltage is 18, then that must equal V1 plus V2 must equal 18. So instantly I could use the voltage drop law, but I like to leave the voltage drop law to check. I could use Ohm's law there to actually find out that the voltage drop across the 10 ohm is total current because the entire 1.59 amps flows through him multiplied by resistance, which turns out to be 15.88. But, okay, let's just go, all right. the total less that number should give what that number is because it's in series. And so V total must equal V1 plus V parallel. Okay? So I would use Ohm's law and then go, let me just check. Does 15.88 plus 12.12 equal the total? Yes, it does. Tick. I know I've got the right answer. And then I can move on and use Kirchhoff's law to find I1 and I2. So that's going to be V on R. That's going to be V on R. And the two currents should add up to the total. All right. So you use Ohm's law in each channel now. So you can go away and find the current through channel 1 and the current through channel 2. To check you got the right answer, you add them up, it should be 1.59. Alright, go and do that before you disappear. Cool? No wuckers. Did everyone get that? Gentlemen, did you use Kirchhoff's law to confirm that, let's just say, I1 and I2?
Equals each other.
Good. And again, you could use the ratio method, but it's not preferable. Use Ohm's law. By the way, Cooper, tell me what is that one? Yes.
These two already add up to 1.59. So that means it's not
0.53, and then down here 2.12 over 2 must be the
1.06.
well, I could use Kirchhoff's law to cheat and go it's 1.06.
Yeah, but you add that together and you get 1.59.
You just use Kirchhoff's law to check that your answer is.
We still haven't added that one's current.
No, he's in series. So the total current flows through 1.59, and then when it gets to here, 0.5 goes up that way, and 1.06 goes through that way, and then they recombine to 1.59.
Okay, so that's done. That's a done answer.
Yeah. Yeah.
I'm gonna get lunch now.
Yeah, come back, please. Uh-oh. Hang on. Hang on. I don't want to open it. Hang on.